Okay, thank you for that. We'll get started here. So I wanted to kind of talk about the structure of the talk real quick before kind of jumping into the details. So uh, like like we just talked about, I'm going to be defending my thesis within just a couple of months. So a lot of what you're going to see today is going to deviate maybe from the standard seminar in that I'm going to be focusing really heavily on methods and kind of the results that came from what I've been working on research wise. But if you feel like I haven't answered the questions of, okay, what do those results mean? That's because I'm kind of saving them for the thesis defense. And then also, this is going to be a two-part talk, and the two parts are going to be a little bit heterogeneous, excuse me. Uh, so we're going to start with like a long-term boundary layer evolution talk, and then about halfway through transition into a severe weather case study. And I think you're gonna see the transition because it'll be pretty obvious. So with that, we're going to get into talking about boundary layer evolution across long-term data sets. So those of you who know me know that I'm a big clamps guy. I work with the BLISS team, so I have the opportunity to work with clamps data sets quite often. Those of you who don't necessarily have as much experience with clamps, this is a good chance to get to kind of give an overview. CLAMP stands for the Collaborative Lower Atmospheric Mobile Profiling System. And when I did the first couple runs of this talk, I was bragging about how within the past few months, I finally figured out what that acronym stands for. And then during my third or fourth run through, I noticed that I'd forgotten the word mobile. So I was talking about CLAMPS. So CLAMPS is an OU0 NSSL profiling collaboration. There are two different CLAMPS trailers. They're mobile profilers, which is really cool because they can actually be run remotely. We don't need someone there to generate atmospheric profiles, and they can run over long terms. So we can get kind of high resolution, rapid atmospheric profiles, both kinematically and thermodynamically. But we don't just get them over the course of hours or days. We can get these profiles over the course of weeks or even months. Clamps, both of them are outfitted with both thermodynamic and kinematic profilers. So the thermodynamic ones, there's an ARI, which stands for Atmospheric Emitted Radiance Interferometer, which is, along with the microwave radiometer, they both kind of work in similar ways where using upwelling radiance and then kind of the downwelling return, we can sort of create a best guess of what the thermodynamic composition of the atmosphere looks like, because the downwelling returned radiance has cues. The amount of a certain wavelength that's returned can tell us sort of about the atmosphere's thermodynamic characteristics. And then both clamps are also outfitted with a Doppler LiDAR, which is kind of becoming pretty common these days. The LiDAR is essentially like a radar, but with light. So it sends up a laser, which can reflect off of boundary layer aerosols, and the return can give us a 3D profile of the horizontal and vertical wind components of the atmosphere. So both clamps have been involved in quite a few campaigns, beginning with Pecan way back in 2015. And the pace of deployments has really picked up in recent years. Both clamps are currently involved in perils. You can see this image I took at 5:30 a.m. before I'd had my coffee in Yazoo City a couple of weeks ago. So the upshot of this is that we have a bunch of clamps campaigns that have occurred across diverse seasonal regimes, spring in Mississippi versus winter in Crested Butte. And that also gives us a bunch of climate regimes, such as Oklahoma, which is kind of, semi-arid, or Wisconsin, which is continental. So there's a bunch of heterogeneity across these long-term boundary layer data sets that we now have the opportunity to begin comparing one to the other. And so that kind of brings me into the opportunity for some boundary layer research via the CHEESEHEAD project. CHEESEHEAD stands for this down here. If I haven't learned the CLAMPS acronym, the CHEESEHEAD acronym is probably never going to happen for me, but that's okay. More importantly, I consider my research's patron saint to be Clay Matthews wearing a CHEESEHEAD hat. So the opportunity via this CHEESEHEAD project, which occurred in 2019 in northern Wisconsin, the idea was that this would be an intensive collaborative campaign across a bunch of boundary layer institutions that could quantify surface fluxes and how the energy balance works across seasonal differences in the land regime. But what we could do with clamps is we could kind of start to take these long-term data sets and average them. So instead of having 2 months worth of daily atmospheric profiles that we could put time height cross sections across 2 months, we could average all of them into a composite daily boundary layer. So a 24-hour, average time height boundary layer cross section. And then we can start to compare those composite boundary layers with one another to start seeing how boundary layer evolution compares across these different seasons and different locations. That was kind of the original opportunity outlined via CHEESEHEAD. And then NSSL and also the weather gave us a new opportunity to do some research. So the CHEESEHEAD domain, it's worth noting, is right about here. And on the afternoon of the 19th of July in 2019, the CHEESEHEAD domain was basically run over by a derecho that occurred. You can see kind of right here, it went right over. And also this renegade supercell out in front of it that we'll talk about later. So there was this derecho supercell merger, and then the next morning, the outflow boundary returned from this MCS returned northward, and in this area there was a localized tornado outbreak. So we'll talk more about this second opportunity later, but we have a chance to compare the boundary layer evolution that we found across the whole summer in Wisconsin with the boundary layer evolution on the 2 days of this severe weather event. And we can also evaluate the warn-on forecast ensemble. We're going to get into that later, but first we're going to do the boundary layer comparison. So I talked about how I was compositing data into kind of this 24-hour average boundary layer evolution. First thing to do to be able to compare composite boundary layers was to decide which campaigns to use data from. So because I was funded through the CHEESEHEAD project, obviously I was going to choose the CHEESEHEAD campaign, which kind of occurred right in this square right here. And both CLAMPSs were there in the fall of 2019, so I used CLAMPS data sets from that. I also used data set from the summer of 2019 in the CHEESEHEAD domain from a similar profiling platform operated by the University of Wisconsin. And then that kind of gave us the opportunity to compare the boundary layer in Wisconsin in the summer compared to the fall. And then to get a summer comparison, I pulled a CLAMPS campaign that occurred in the summer of 2020 in central Oklahoma. So we can kind of compare summer Wisconsin versus summer Oklahoma. The next challenge that I had was to choose what atmospheric variables to composite. And this was a tough one because anyone who's taken one of Scott Zalewski's classes knows that there are a lot of boundary layer variables. The three that I settled on are static stability. So essentially the, kind of a thermodynamic composition of the boundary layer. Vertical velocity variance, which is shown in the bottom panel right here. Vertical velocity variance gives us a rough proxy for turbulence within the boundary layer. So this is kind of a turbulence comparison. And then moisture transport, which is, a rough proxy for the low level jet. So those were the three composite variables that I compiled across the three campaigns. The final challenge that I had, and this was kind of a unique one, was that I couldn't just stack up all the data sets on top of each other to compare them, because sometimes observations on one day might be taken at 519 UTC, and the next day at the same height level, they were taken at 520. So the challenge was to composite data that wasn't consistently timed across days. And the solution to that was basically to take an hourly bin. So I kind of have outlined the bin from 5 to 6 UTC based on this one day that occurred in the Wisconsin fall data set. And you can sort of see if you look in here that there's the height levels become more coarse. So every observation that occurred at this height level between 5 and 6 UTC was averaged to create kind of an hourly composite, which was then put into a nice little contour F to make a total composite characterization of the boundary layer. So those were kind of the methodological challenges and steps that I took. Now let's take a look at kind of the methods for each individual variable and the results that ensued from them. We'll start with static stability, which had its own unique idiosyncrasies. First, I want to note that I took static stability for the composites from one height level to another. So there wasn't any like running average. This is just instantaneous static stability from one bin to the next. And then you'll also note when you look at them that they go on the y-axis from 300 meters to 2 kilometers, which might seem kind of weird. But if you note the data below 300 meters, it succumbed to what I am scientifically referring to as thermodynamic retrieval method wonkiness, which essentially they just struggled to deal with super adiabatic boundary layers. The retrievals did. There was kind of a setting in it that didn't really like to deal with it. And so it just made the data unusable. So we're going to go from 300 meters to 2 kilometers. And 2 kilometers I chose because thermodynamic retrievals kind of have lower quality above the cloud base height. And we're trying to stay within the boundary layer anyways. So we'll start with a Wisconsin seasonal comparison. There are really 2 features of note that we're going to look at here. And the first one is really obvious if you look in the summer Wisconsin data set. It's this daytime convective boundary layer that you'll note basically it reaches static neutrality in Wisconsin in the summer. It doesn't get quite as unstable in Wisconsin in the fall, but reaches a similar depth. And we do still have a pretty well-defined convective boundary layer. And then the other feature that's kind of worth noting is this residual layer that develops overnight. And you'll note that the residual layer lasts basically until daybreak in Wisconsin in the summer, and it kind of lasts until midnight or so in the fall. So this is kind of intuitive. In the summer, we're expecting to get more incident solar radiation. With that, we're probably going to expect to get more vertical mixing and a more statically unstable boundary layer. So this kind of makes sense that we have a more unstable boundary layer and residual layer in the summer than in the fall. I found the summer comparison to be actually quite interesting, though, because you'll note Wisconsin's on top and Oklahoma is on the bottom. Once again, we have this, really unstable convective boundary layer in Wisconsin. In Oklahoma, the boundary layer doesn't really develop anywhere near as much a degree of static instability. So it's a much more stable boundary layer in the afternoon. It reaches up to maybe a higher depth, but similar depths, and develops later in the morning into the afternoon. And then there's almost no evidence of a residual layer in Oklahoma in the summer, while we have this really well-defined statically less stable residual layer in Wisconsin in the summer. So that's kind of interesting because I assume that Oklahoma would be more unstable because it's further south and we're kind of a semi-arid we have a semi-arid climate regime here, but that's not what ended up happening. The key takeaways are that we kind of found what we would expect in Wisconsin seasonally comparing the boundary layers. There was a less stable boundary layer in the summer than the fall, but the location comparison between Wisconsin and Oklahoma was really interesting because the boundary layer and residual layer were a lot more stable in Oklahoma than in Wisconsin. All right, we're going to pivot now to vertical velocity variance. Like I said, this can roughly be considered turbulence. And I've included an example from one day in Oklahoma in the summer 2020. You can kind of see a couple features. First of all, the fuzziness aloft, that is basically above the boundary layer. So what vertical velocity variance can do is it can show us the height of the boundary layer. Other people are kind of focusing on that. I'm more interested in the magnitude within the boundary layer. So my method basically filters this out and turns all this like fuzz on each day into a nan. But what that does mean is that if the boundary layer reached 1.5 kilometers on a certain day at 19Z, that might be the only observation that doesn't get turned into a nan when we go through and create the composite. So the mean variance was only taken at height bins and within hourly chunks that had 5 or more observations to kind of maintain integrity of the data set. And then I wasn't able to use LiDAR observations from the fall Wisconsin data set. Both CLAMSAs struggled to pick up aerosols in the upper boundary layer, and I can't really explain why because that doesn't really fall within my area of expertise. But it does mean that the fall Wisconsin LiDAR data set wasn't used for this analysis. So we're just going to have a summer comparison. And it's really quite interesting because I would expect from the fact that in Wisconsin we had a more unstable boundary layer, that in Wisconsin we would have a more turbulent boundary layer because turbulence kind of leads to convective mixing, and they kind of would seem to play on one another. But instead, in Oklahoma, we had earlier developing, stronger, and deeper turbulence than we did in Wisconsin. Basically, in every way, the boundary layer was more turbulent in Oklahoma. So that's really counterintuitive, and that counterintuition lasts all the way into the evening when Oklahoma has a deeper, longer lasting, and more turbulent residual layer than the one that was noted in Wisconsin. So basically, the static stability and vertical velocity variance analyses were completely contradictory to each other. And I thought that was really interesting. We'll talk more about that in just a second, but I want to pivot to the moisture transport comparison before we do that. This analysis methods for moisture transport were pretty simple. Like I said, moisture transport I'm using as a rough proxy for the low-level jet, since that's kind of one of its more important functions. And I just defined moisture transport by multiplying the U and V wind components by water vapor mixing ratio. And again, there were no fall observations because the LiDAR was struggling to deal with aerosols in the upper boundary layer. So we're just going to get a summer moisture transport comparison between Wisconsin and Oklahoma. Oh, sorry about that. The first thing that's really stands out to me when I look at the summer comparison is that we have a noticeable maximum in meridional moisture transport in Oklahoma in the summer around 5 UTC in the middle boundary layer. We all live in Oklahoma, so we all know that's the nocturnal Southern Plains low-level jet that we get most nights in the summer. And then there's maybe evidence that the low-level jet zonal branch peaks closer to daybreak, but it's a little bit fuzzier and harder to tell. But we have this really well-defined meridional low-level jet and a possible zonal branch peaking later in the evening in Oklahoma. What's interesting is that we have a noticeable peak in Wisconsin's moisture transport shortly after sunset in the zonal direction. Meridional transport was basically zero throughout the whole day, which was pretty impressive to me. I actually had to redo this 4 or 5 times to make sure I wasn't doing anything wrong. But what's interesting is that we might have the presence of a low-level jet kind of being hinted at here in the zonal component in Wisconsin in the summer. And so the quick takeaways here are that we have a largely meridional low-level jet in Oklahoma in the summer 2020. That's not, anything new or groundbreaking. We know that should be there. And there's also evidence of enhanced zonal moisture transport at night in Wisconsin, which is pretty interesting because remember, we're all the way up in the northern part of Wisconsin. So the key questions that I have from the boundary layer comparison are, why didn't we have matching results from the static stability and vertical velocity comparisons? Vertical velocity variance comparisons. Why were they counterintuitive? And then if that was a low-level jet that we found in northern Wisconsin, is that within expected climatology, or have we found evidence of a low-level jet maybe where we wouldn't expect to see it? And I'm not going to answer those questions right now, but I will note that if you attend my thesis defense in a couple of months, I will be discussing those topics further. Okay. Now we're going to pivot to the warn-on forecast, severe weather outbreak analysis case study. So boundary layer people, there will be kind of some boundary layer observations and influences in the middle, but convective people, you can get excited. This is your time. So before we get into kind of the methods, I want to give a quick overview of the warn-on forecast system. It's an ensemble convective allowing model that's operated by NSSL. It has 18 individual members, 6 for each of the 3 kind of major boundary layer parameterization schemes, MYJ, MYNN, and YSU. And it has a shifting domain, which is really cool. So basically, NSSL can put the WAFS domain wherever they think the greatest severe weather threat is that day. So in this case, when we have a derecho going through Minnesota into Wisconsin, the domain was focused over northern Wisconsin. But if we had, say, a severe weather event in central Oklahoma, NSSL could put the WAFS domain basically right over our heads. So it kind of can be used to support operations in the short term for whatever kind of severe weather event we have going on. So that kind of leads us into an event overview of the 2-day severe weather event that occurred. You'll note from the severe weather reports on the 19th of July, there were actually some tornadoes that occurred in western North Wisconsin. When this radar loop wraps, you'll see why. There was this renegade supercell and kind of a couple of mesovortices within the derecho before it kind of went more traditionally outflow dominant as the supercell and derecho merged. So we went away from a tornadic threat to more of a wind damage threat. And actually, just east of Rhinelander, which is right here, where that supercell went outflow dominant and merged, we had an event that's known in the upper Midwest as a blowdown, which is where a bunch of trees get blown down. And so that was kind of an interesting opportunity for study because Rhinelander and Prentice is near Prentice, which is right here, which is where we had a radar wind profiler. So really exciting opportunity. And then to kind of finish off the event overview, I'll kind of note that there was a big severe weather event that occurred the next day, and you can kind of just see a bunch of wind reports. But the ones that occurred in Wisconsin in this axis actually happened mostly between daybreak and noon. So it was kind of a unique situation where we had this MCS still in the picture at midnight, and then by daybreak the next day we were already going into a localized tornado outbreak. So we have a couple of research opportunities here. We have a chance to look pre-storm before this supercell MCS merger and kind of see how WAFs would have handled that. And then we have an opportunity to look post-MCS at how WAFs handled the outflow boundaries, southward motion, and then eventual location where the severe weather threat was the next morning. So starting and looking at kind of the pre-storm verification, I'll note that at 21 UTC, WAFs had 6 of its 18 members correctly predict that there would be a renegade supercell out ahead of this derecho. And this is pretty cool because this supercell is going in this picture pretty much right over Prentice, which is where that radar wind profiler was. So we have a chance to look at how WAF's boundary layer wind forecasts, and actually I looked at initializations to see, you know, what a forecaster who was trying to figure out what would be happening in the moment, what they would be looking at. So how WAF's boundary layer wind initialization profiles compared to the actual Prentice radar wind profiler. And I apologize because in the next like 3 minutes, I'm going to say profile another 15 or 20 times. For this, the Prentice wind profiler collects data over 55 minutes, which was then averaged for that valid hour. And I basically compared the Prentice radar wind profiler data to the WAF's initialization for that hour. I had generated comparisons at 21, 22, and 23 UTC. If we go back, you can see this is at about 020. So I wanted to do a 0 UTC just before the storm arrived comparison. But this is what the radar wind profiler photograph looked like. So I didn't really think that it was going to work. I spent a whole day wondering what was wrong with my code before I realized that I was trying to do a photograph analysis inside a supercell's RFD. So I compared basically 2 different ways. Wind profiles like this, and then I also will look at photographs in just a second. On the left, we have of these two panel displays, we have the Prentice wind profiler, and on the right, we have WAF's initialized wind profiles from 21, 22, and 23 UTC. So you can kind of take them as 3, 2, and 1 hours before. The general shape and character of the profiles was pretty similar between observations and WAFs. You know, we're kind of in the right general vicinity. But WAFs had 2 key errors that I think we can see may have influenced how it was initializing boundary layer wind profiles. The first and most noticeable is that WAFs was really developing too deep a wind of this, or too deep a region of this backed surface U component. So there was a negative U component near the surface, or we consider them backed winds in the wind profiler data. But WAFs was at times making those backed winds go all the way up to 1.75 kilometers, whereas in reality, the region of backed winds was maybe only a kilometer deep. So there was too deep a region of negative zonal winds. And then the other major error that WAFs was developing was that it had, we kind of had this largely uniform meridional wind component at 21 UTC between both the wind profiler and the initialization on WAFs. But by 23 UTC, WAFs had developed this strong region of low-level meridional wind shear that the Prentice radar wind profiler really didn't develop at all. So WAFs, as we got closer to the supercell approaching, had way too much meridional wind shear. And you'll see how this plays out now in the photographs. Looking at these, this is 21, 22, and 23 UTC again. The red and blue photographs you see here, those are both the Prentice radar wind profiler. So those are kind of the observations. And then these clustered together ones are WAFs. So you'll see we have the general shape and character of the photograph pretty much the same between WAFs and the radar wind profiler at 21Z. But by 22 and especially 23, WAFs kind of goes like mega, wow, we have this crazy supercell wind profile. This is something that we would consider favored for possibly significantly tornadic supercells. But in reality, the photograph shape didn't change all that much at the Prentice radar wind profiler. It just kind of shifted a little bit. So Prentice would give you something that's favorable for maybe an outflow dominant supercell or a weakly tornadic supercell like what we saw in reality. But if you were looking at WAFs initializations, you would probably be expecting an inflow dominant or possibly significantly tornadic supercell. And that can obviously be a big problem if you're a forecaster and you're trying to, get the most up-to-date information. I also want to quickly note that there may have been some boundary layer impacts on that supercell MCS merger. You'll remember from the first part, we had a really, really well-mixed boundary layer most days in Wisconsin right at the Prentice site. What ended up happening on that day, note that this isn't a static stability anomaly on the 19th of July. This is just a potential temperature anomaly, but we can kind of infer static stability from the vertical gradient of potential temperature anomaly, which there isn't much of a vertical gradient, which would lead us to believe that we were in a pretty standard well-mixed boundary layer at Prentice that day. So if we had a well-mixed boundary layer, that's pretty well known to be conducive for strong outflow winds. So there may have been some boundary layer feedbacks that help play into the blowdown that occurred. Okay, so now we've kind of looked pre-storm and pre-MCS supercell merger. Now we can kind of go into outflow boundary verification, which is a fun thing that I've been working on lately. You'll note this is actual observed dew points from basically 0 to 14 UTC. So from the time the supercell and MCS merged all the way until the localized tornado outbreak started going on. You'll see the boundary is sagging south and southwest across eastern Wisconsin, and there's a synoptic cold front doing the same across Minnesota. But if you look in between them, the boundary really isn't sagging that much south. And in fact, right before the event occurs, you can see a little bit of northward return of the outflow boundary, which is pretty interesting. So the research opportunity here is to see, did WAFs handle that southward motion and then stall or northward return well? Or did it kind of, have issues with handling that? And then why did that outflow boundary not keep flowing south? Why did it stall? And why did it in places return north? And were there boundary layer processes that may have influenced its motion overnight on the 19th to the 20th? So the first thing that I had to do was figure out how to delineate an outflow boundary based on, observations, which is really easy to do if you're a forecaster and you're drawing your line in place, but a little bit harder to do when you're trying to delineate a boundary in Python. So I kind of used a fuzzy logic method that really heavily relied on moisture gradient and mass convergence, especially, to figure out where the outflow boundary would be in reality. This is the observed surface dew point at 6 UTC on the 20th, and this is how my algorithm came out with the boundary. I'm pretty happy with its performance. Obviously, it's pretty coarse. You wouldn't expect a depiction of a boundary to be that wide, but we only have so many observations within the network, so there's only so much you can do to make your boundary finer without introducing possible errors as a result of just data availability. It was a lot easier to delineate the boundary with a high degree of precision using WAFs because it has a 3-kilometer grid resolution. But I did use a similar fuzzy logic gradient method, and you'll see the moisture gradient and mass convergence would really be pointing right in here to where the boundary is. And I did that for all 18 members of each WAFs run. And I used an ensemble probability, basically, that each member would have the boundary at a certain grid point and divided by the total number of members within the ensemble. And that ensemble probability defined the outflow boundary that you can see down in this panel. So we have a higher resolution and higher precision, but I want to make sure to clarify that that's not necessarily higher accuracy. So the next thing to do is basically just to calculate boundary error between WAFs and actual observations. I found the maximum ensemble probability at each longitude grid point along WAFs between 88 north and 94, or 88 west and 94 west. This lake breeze boundary kind of caused some issues with verification, so I wanted to make sure to just focus on areas where we weren't kind of having that feedback. And then I basically, at that longitude grid point, I found where the maximum ensemble probability was, and I subtracted it by the distance to the nearest actual boundary location. So a positive bias is going to show that WAFs was too far north with the outflow boundary. And a negative bias is going to show that WAFs is too far south with the outflow boundary compared to observations. Now, I can't really show all of the actual errors like this because I did this for every valid hour between 1 UTC and 14 UTC, so 14 valid hours. And WAFS runs for 6 hours, so there's 7 runs between the initialization and that 6 hours for each valid time. But I want to note a couple of trends. First of all, this is average error between 88 and 94 west, and you'll note that error almost always is under 30 kilometers, which is really impressive and speaks to the utility of WAFs to the forecaster in this situation. But there are a couple of trends. Early on in the evening, when the boundary was headed south, we largely had either no error or in some cases positive error. So that would argue that WAFS was a little bit conservative with the southward motion of the boundary in the early overnight period. And then as the boundary started to stall or return northward, WAFS started to develop much greater magnitudes of boundary error, and those magnitudes tended towards negative. So WAFS was being too conservative in stalling it, or being too conservative in its northward motion by, ending up too far south. And the final thing I kind of want to point out is that boundary error did not decrease with decreased lead time. So that's kind of what I expected going in, because I'm not a data assimilation expert. Pat Skinner has told me that that's pretty, to be expected. But what can be seen is that in cases where initial error was already great, and the reds are all minus 25 or less, so 25 kilometers to the south or more, and blues are all anytime that WAFS was greater than 0. I should have specified that much earlier. I apologize. But if we had a big miss early and we were in the red, so 25 kilometers to the south or more, we tended to stay in the red. So WAFS kind of tended towards inertia, and there was kind of a high autocorrelation in WAFS forecasts from hour to hour, even all the way to the 0-hour initialization. So the big takeaways here are that largely, especially towards the end of the evening, the WAFS forecast outflow boundary was to the south of the boundary in reality, and that boundary error did not improve markedly with time. So it didn't really decrease with as we got closer to the 0-hour valid time. And I want to look at one final thing before we kind of start to wrap this up. The moisture return may have had some sort of boundary layer influences. This is 850 millibar winds and water vapor over the course of the evening from WAFS initializations. You'll note that there's a pretty strong low-level jet over much of Iowa at the time. And those of you who know Iowa and southern Minnesota, this is corn growing country. So it makes sense that there's kind of a moist reservoir at the beginning of the evening across this area. And so the boundary kind of stalls when it runs into this low-level jet. And we have this moist reservoir that's in place right as the supercell tornado outbreak that occurred the next morning happens. So it's possible there was some sort of land atmosphere feedback with the low-level jet feeding moisture back into the system. And that's not something that I want to necessarily say definitively, but it's something that I'm going to be looking at in the next little bit. So the key questions here are, did WAF's boundary layer forecast kind of undersell the potential for the blowdown by maybe overselling the potential for supercells with their initializations compared to the Prentice wind profiler? Was it maybe favoring the supercell mode too much, and that would have led us to miss what actually happened? And then how important was the role of the low-level jet over the night on the 19th of July in transporting moisture back northward and maybe blunting the southward progression of the outflow boundary? I don't want to necessarily answer those questions now, but again, my thesis defense should be in just about 3 months. And so attend that, and I'll kind of be discussing those topics further. I just gave away my funny finish. Whoops. Okay, so in summary, the long-term boundary layer data set comparison, we can see that in Wisconsin in the summer, we had a more classically unstable boundary layer than Wisconsin in the fall. And we had a more classically unstable boundary layer in Wisconsin in the summer than Oklahoma in the summer, but Oklahoma in the summer had a more turbulent boundary layer. And then there was a possible low-level jet as far north as northern Wisconsin in the summer based on remote profile data. And then in the severe weather case study, WAF's wind profiles initialized really overestimated low-level wind shear compared to the radar wind profiler. And WAF's was a little bit underreactive or conservative in outflow boundary advancement to the south, and then its return back to the north. Okay, now Clay Matthews and I are ready to answer questions.
Okay, yeah, really, really cool stuff, Nolan. I'm curious, looking back at your slides on the vertical velocity variance profiles between Wisconsin and Oklahoma, and I'm
Yeah,
wondering
pull
if you
those up.
have any more insight on why those two were so strongly different, maybe from the perspective of like a TKE budget or something.
I have not necessarily looked at it from a TKE budget perspective. I've actually been considering it more from a convective instability perspective.
Okay.
So looking at it in a TKE perspective might be a good idea to kind of solidify the results, but I kind of have some I have a pretty well established theory as to why this happened, but I don't want to comment on it too far because that's kind of, like I said, getting into what happened. But to answer like the specific of the question, I haven't looked at this from a TKE perspective.
Cool. That's all good. I see Petra's comment. I think that is that makes sense to me. It is definitely windy here. Thank you.
Yeah, Nolan, I think that probably plays a role. I don't. Did I miss? Did you show a comparison of the horizontal winds? I may have missed it. I was juggling a few things. Or are you trying to keep that a secret until the defense?
No, I haven't. I did not show just a straight horizontal wind component comparison. That is something that I do have on file and I've looked at, but I didn't show it in this talk. And that's not necessarily something that I was hiding. It's just something I didn't include.
Yeah, my guess is that plays a role in why you see so much, why your vertical velocity variance is so much higher.
Okay, yeah.
Differences in the horizontal wind probably play a role.
That makes sense. That's something that I'll definitely go back and look into as I'm kind of working towards polishing up this research and, yeah.
In some sense, you might think about coming up with a way of scaling your vertical velocity variance by the horizontal wind and doing a comparison then. So like a sigma W over some kind of scaling velocity.
Okay. Yeah, I can do that.
So, yeah.
Sure.
It's almost like a turbulence intensity, but you only have the sigma W, you don't have the whole TKE. But that will be interesting to see.
Okay, I'll definitely go through and do that.
And as usually, I forget to first say nice talk. So,
thank you.
And I'm gonna hop off now, but really nice talk.
Hey Nolan, great talk. I had one real quick question about WAFs and then a little bit more substantive one. Did you run for the comparisons of the outflow boundary evolution? You just ran further data simulation and forecasts out past the normal ending time of 04Z. Is that correct?
Yes. Yeah. We ran the model all the way out to 14Z.
Okay, and so it included data simulation too. So you kept issuing 6-hour forecasts every hour from out till 10 or 14Z, I guess.
Correct.
14Z.
Correct.
Yeah. Okay. That makes sense. I was just wondering, because I guess the boundary conditions would be getting a little stale there. I don't know that it would be really affecting things too much, but just noting sort of the character of the change there for some of the later initialization times, I wondered if that may be contributing. But then my main question was back to the supercell and the hodograph structure. So one thing that was neat about the supercell, I think, is that it was riding a warm front.
Yes.
And so just sort of poking through some of the WASP forecast soundings, you do get a pretty big change in character of the hodograph if you're north of the warm front or south of the warm front.
Mm-hmm.
And so I was wondering if you had checked to see is the WAF's warm front, or is the supercell relative position to the warm front the same in the observations as it is in WAFs? And if it's possibly on the cool side of the front in WAFs, is that one reason why you're seeing a much larger photograph, especially in the low levels?
I actually did do that analysis back in the fall, and
Mhm.
what I found is that WAFs and the HER were both generally too far north with the front, but in pretty much under any definition, the supercell was north of the strict warm frontal definition. So like this was something that occurred on the cool side.
Okay.
And WAFs would have had it on the cool side, and that kind of makes sense because this looks like a cool side profile. But the radar wind profiler was also picking up something that was actually probably even further to the cool side than WAFs expected.
Okay. And so if you made the photograph comparison boundary relative rather than in a fixed location, would you see a greater similarity in the WAFs and the observed profiles, or do you think that it would be still an overprediction in WAFs?
I would expect it to still be an overprediction because the WAFs wasn't missing by too much.
Right.
I can go pull the warm front verification that I did back then. It was a little bit more subjective, so I didn't include it in this talk. But I would think that, especially since you'd expect to see the largest photographs closest to the front, you might see a little bit of a shrinking of the photograph if WAFs knew that this was further from the front than it thought. But I don't think it would be enough to overcome the pretty large differences in shape that we saw.
Okay. Yeah, no, that makes sense. Just curious.